Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge, Knight Dialer. So basically we have sort of a chess knight, so just similar to chess, where basically a knight can move in L shape. It can be either first two step horizontally and then two steps vertically, one step horizontally, or the other way around, two step horizontally and then one step vertically. Right? But the start is two steps and then one steps and sort of gives you an L shape. Now the variations they add on here is that you have sort of a phone pad where you can stand on numeric cells, right? And so with this phone pad, you need to apply these L shapes movements. So that's the key idea here. And you get N. And basically what we are trying to get is how many distinct phone numbers of length n we can dial. So if n is equal to 1, how many distinct numbers of length 1 we can dial. If n equal to 2, how many distinct of length 2 we can dial. So basically n is the number of digits. And initially you can start in any numeric cell, okay? And so you start from a numeric cell and then you can do n minus 1 jumps. It makes sense because you need n digits. When you start in a numeric cell, you have the first digit, and so the remaining ones are n minus 1. Okay? And the jumps you are allowed to do are only valid knight jumps, so only something like this, or something like, let's say, if you are at 4, like this. Okay? And we need to give the answer modulo 10 to the power of 9. So let's take a look at the first example here. N equal to 1. What are the possibilities? Now, the key thing here to remember is that you need all the variants. So what does that mean? That means one possibility is to start at cell 1. The other possibility is start at cell 2, start at cell 3. So each digit you can start at it and then calculate the number of distinct phone numbers you can get from that cell. So with n equal to 1, which means basically just one numeric value, well, the distinct one you can get are all the numbers here. So you can start at 0, at 1, all the way to 9. So overall, that's 10 numbers, or 10 phone numbers, so 10. Okay. For n equal to 2, it's a little bit different. Well, for n equal to 2, you can first start from 0 and then figure out all the variations. So that means you start from 0, let's say, and then you go 2 to 6. Or you can start from 0, go to 4. Okay, so two possibilities with 0. That's the only possibilities because you can't go left or right. For 1, you can go, for example, like this to get to 8. Or you could go like this to get to 6. Those are the only two possibilities. And if you do all of those, you get 20 at the end. Okay, so that's sort of the idea. And the bounds are 5,000, so not too big. So it should be doable. Now, how do we tackle this? Well, the main thing to think about here is that this is actually sort of can be done recursively because let's say when you are at, for example, if n equal to 3 and you start here, you get to 6, you get to 4. Now you use 2 out of that 3. So you have one more jump. So now you do 6, which you can only do like this. Okay, or maybe you could do like this. Okay, 6 you could go to 1, you could go to 7, or you could go to 0 like this, back to 0. Okay, and so for 6, so basically that means when you get to 6, now you are at 6 with the jumps 1. So you can see there are sub-problems, basically, that's what I'm trying to say. Now, what is the state of a sub-problem here? Well, first, the current square you are at, but also how many jumps you have, so the remaining jumps. Okay? And for, let's say, n equal to 3, let's say we start first at 0, we have 2 remaining jumps, okay? And so we go to 6. So when we go to 6, now we are at cell 6, we have 1 remaining jump. We go from 6, we can go to 1, and we have 0 remaining jumps. And so what's the overall number here for this 0? 6, 1. Okay, and you do the same thing for other numbers. So then you start from 1 and you try all the possibilities. Of course, starting from 0, you have another possibility, which is to go to 4, right? So you can go to 4, and then you have one remaining jump. Okay, so this is clearly is a dynamic programming recursive solution. Basically, our state here is going to be this. Okay, and for each for each number, we know the valid numbers it can go to. That's the key insight here is, for each number, you can only go to specific places. So for example, for 0, you can only go to 6 and 4. For 1, you can only go to 6 or 8. Sorry, to 6 like this or to 8. And so let's just have a map with this. So let's have a map. Let me just copy it over. That says for each number, what are the valid places you can go to. And now, when we are, let's call this DP, then for each number, we just need to get the next squares we can go to. Basically, let's call this valid jumps. Okay, then we can just check the valid jumps for that current square and go to those. And of course, from that next one, we need to decrement the remaining jumps by 1, right? Because we just utilized 1. And that's pretty much it. We can, of course, cache, because there will be repetitive states. Because, for example, 6, you can get to it from 0. You can also get to it from 1. So we don't need to calculate it multiple times. So we can just cache our DP here. Okay? The other thing is, what is our base case? Well, base case should be if there are no more remaining jumps, right? We are done. And when we don't have any remaining jumps, that's one way. We found a valid way to get to a number of length n, so we can just return 1. And the result here needs to add up all the different ways, right? And that's what we return at the end. Of course, we will need to do modulo, but that's the idea here. Now, the next thing to think about is we can start on any numeric cells. So this one needs to be called, the start point needs to be 0 with 2 remaining jumps, 1 with 2 remaining jumps, 2 with 2 remaining jumps, 3 with 2. So basically from 0 to 9, we need to try all of them as a starting point. So that's something we need to take care of in the code. But that's the core idea, so let's just implement it here. So what do we need to do? We need to define our function, so we need current square and then remaining jumps. Let's just copy over what we just did, like this. And we need to cache, so this needs to be a cache here. And we need to define our valid jumps map. So this is going to be like this. You could also use an array because the indexes, because the values here are consecutive. You could use an array if you want to. So we have our valid jumps array. And then here we said we need to try every number as a starting point. So start, let's call it, in the range of, we need 0 to 9, so we can just do range of 10. And so that's going to be DP of that start point. Remaining jumps are just n minus 1 because we already utilized 1 by placing the number in the start position. Now what do we need to get? We need to get all the different ways. So we need to add up each one of these. And then we need to return that. Okay? Let's call this ways just so that it's clear. Same thing here. And then we need to define our mod. So our mod that we need to do, we need to mod by for each addition. So it's going to be 10 to the power of 9 plus 7. And then we can just, here, this is going to be ways plus. And we need to apply modulo. Same thing here, we need to apply modulo. Like this. Okay. And that pretty much is it. So let's run it. And make sure it passes. Looks good, let's submit. And that gets accepted, okay? Yeah, so that's pretty much it. The key idea is to figure out that you can actually just hard code this possible state for each number. And then from there, you could do a recursive dynamic programming solution. Yeah, so that's pretty much it. If you need one-on-one coaching, feel free to reach out to me on SuperPeer. Yeah, feel free to reach out to me on SuperPeer if you need any help. Thanks for watching, and see you on the next one. Bye.